Welcome to Science at the Theater's 5 Big Questions, sponsored by the Friends of Berkeley Lab. My name is Jeff Miller. I'm Head of Public Affairs at the Lab, and I will be your host for this evening. Now, we have a few special things planned. There will be a voting segment at the conclusion of all the presentations in which we will ask you to vote for the question you think science should answer first. We'll also have all the science presenters up here on stage in a Q&A session. There are mics 2 on this level and 2 up above, so you'll have a chance to ask them questions. And then those of you who might not be members of Friends of Berkeley Lab yet and who picked up one of these, there is a spot where you can join. If you do join, you will be eligible. I wonder what that was. You will be eligible for a special lab tour that we will also make available to existing members if you go online next week. So that's another advantage of joining tonight. We hope you will do so. So since this is a night of questions, the first question will be from me to you, which is, how many of you are here for the very first time? Please raise your hands. Great. Thank you so much for coming. A reminder, we will be in Oakland at the Kaiser Theater on April 29th with 5 different questions. We hope you can attend that one as well. Now we're going to kick off the evening by showing the new Berkeley Lab video, which is short by design, just 1 minute and 45 seconds. We hope you enjoy it, and then I'll be back on stage in just a second. Thank you.
Is it possible to make fuels from sunlight? Can we stop breast cancer in its tracks? Save consumers billions of dollars in energy costs? At Berkeley Lab, finding answers to the toughest questions is why we come to work every day. Our science paved the way for medical imaging devices like MRI machines and PET scanners. We added 16 elements on the periodic table, helped develop energy-saving windows, discovered the accelerating universe, and won 13 Nobel Prizes. Scientists from around the globe use our powerful supercomputers to do everything from develop new materials to predict the Earth's climate. We're working to create affordable batteries that enable electric vehicles to go 300 miles on a single charge. Berkeley Lab scientists have even created a solar-powered vaccine refrigerator that could help save countless lives in the developing world. Public service has been part of our DNA for more than 80 years. As a Department of Energy national laboratory, our science is open, ingenious, and humanitarian. It is done for you and belongs to you. The challenges now facing us in energy, health, and the environment won't wait. Neither will we. Our science, your science, will lead us to solutions we can't even imagine. Berkeley Lab, bringing science solutions to the world.
You can apply. You can apply. So the video started with questions, can you make fuels from sunlight, stop breast cancer in its tracks? That was not done by chance. Questions drive science, and questions that provoke other questions keep science alive. In fact, if you think about the word question, you think about the root quest, it's about a momentum, it's about a journey, it's about a zest for answers that scientists and science uses to keep moving forward. So what is the objective of all of those questions? Well, sometimes it's just understanding, sometimes it's a new technology, sometimes it's just to satisfy curiosity, but there are as many questions as there are answers, and as many answers as there are questions. And at Berkeley Lab, questions are our brain food that fuel the discoveries that we really believe serve the public interest. Now, we admit that sometimes the questions can seem a little esoteric, like some on tonight's program, but it's our responsibility to convince you otherwise. And that will not be up to me. That will be up to our panel of scientist presenters, which include David Schlegel talking about dark energy, a very popular topic. Some of you are here to hear about, I'm sure. Yes, I know, it has many fans. Dark energy has many fans. Haimei Zheng was talking about electron microscopy, which you might not think you need to know about, but you really do. Marcus Lehmann on ocean wave energy, Lara Kueppers on the forest and climate, and Leemans on tabletop accelerators. Would he bring his family? Okay. God. Whim, really. Remember to listen carefully because you'll be asked to vote on which of the questions science should answer first. So to start the evening officially, I now welcome to the stage David Schlegel, and his question is going to be, is learning about dark energy going to get us anywhere? David, take it away. Please welcome.
Okay, good evening. I'm going to tell you about dark energy this evening. And for anyone who's my age or older, so 30-ish, when we were in school, this is not something we learned about in our textbooks, but now the textbooks have to include this. So if this is something you haven't learned about, pay attention, because what this is really fundamental understanding in the world of physics that is new. So there really is groundbreaking fundamental physics that we're learning today. So it's really an exciting time for us. The discovery of dark energy was made by two teams, one of them at Berkeley Lab in 1998, so this is 17 years ago. And the discovery was it just seemed like a little thing. What it was looking at exploding stars halfway across the universe. So these are supernova explosions that were just a little bit too faint. They were just fainter than we thought they should be. And you might want to write that off as a curiosity. On the other hand, these people who then won the Nobel Prize because they were smart enough to figure out that, oh, this is important. When you have these little pieces that don't fit, that's your clue. Those are the problems that you really want to be picking away at, because that's telling you there's something in the laws of nature as we understand them that are not right or not complete. And so this was one of those. Okay, and then the interpretation of this was that there's actually too much space between us and these distant objects. So in fact, we actually needed to say the only interpretation that worked was to say that there is more universe between us and these distant supernovae. And so this has changed what we view as the geometry of the whole universe. So we know that it started in a big bang, very bright explosion, don't look directly at it. Then the universe was accelerating, and in fact this acceleration, it was expanding, and this expansion has been accelerating. So that the universe is not only getting larger every year, but it's getting larger by a greater amount every year. And the cause of this is what we term dark energy. Okay. So this effect, it's actually seen in any maps that we make of the universe. So the initial discovery was with these exploding stars halfway across the universe. And since then, we've made many more maps of the distant universe and the nearby universe. And what we do is we make these maps and we try to make them agree with our understanding of physics. And fortunately, there are some features in, this is a map of galaxies where each point in here is a different galaxy. This is actually, I have to admit, this is an artist rendition. This isn't a real map. I'll show you a real map. I'll get there. But I wanted to show this because I don't know if your eye can pick out, there are some kind of circular-like features in these maps. And the universe really has these. It has these giant sound wave echoes from the early universe that have imprinted everywhere in the distribution of galaxies. We can see these. They're large, so they're, okay, the scale here is 450 million light years. So even for an astronomer, that's actually pretty big. And one of the things that we can do, it's a pretty simple geometrical test, is that we know these are sound waves imprinted on the universe, and they should be spherical. Now, if we didn't have something like dark energy accelerating the universe, then these don't look spherical, they actually look squashed. And what we have to do is we have to put in dark energy to make the geometry fit. And once we do that, then these maps make sense. But without dark energy, these maps don't make sense at all. Okay, so the largest maps that we've made to date, they're from this telescope in New Mexico. So this is the Sloan Digital Sky Survey. So this is a telescope where at Berkeley Lab we rebuilt the instruments 6 years ago to make the largest map of the universe, which we've just finished last year. And in fact, all of the data from this telescope, they're publicly released. So if you go to this website here, you can actually find, it's actually every bit of information that we've ever taken with this telescope. So we invite citizen scientists to do whatever you'd like to do with these data. But we've used these data to make the largest scale maps of the universe. And I'll skip the intro here, but once we get going here, now this is a real map of the universe. So this is a fly through three-dimensional space as it really is. So each object you see here is a real galaxy positioned where it is in three-dimensional space. And again, you have to do this accounting for dark energy to make it all map out correctly. But I like to show this map so in case you're ever abducted by aliens and you have to get back to the Milky Way. So I make my kids memorize this. My wife's in the audience here somewhere. She'll attest to this. Okay. So then when we look at the expansion history of the universe, so the Big Bang, again, it was here 13.7 billion years ago. We actually know that figure quite precisely now. So back when I was a student, that number was, well, it's somewhere between 8 and 20. But now we know it to high precision. And this shows the measurements that we've made with this map that I just showed you, where we have a measurement of what the universe was doing 10 billion years ago. And at that time, the universe was decelerating. So there was the Big Bang. The universe exploded, if you will. Gravity is then attracting every atom in the universe to every other atom, so the expansion's slowing down. But then at some point, dark energy kicks in, and the universe starts accelerating. And so we have several data points of the universe accelerating. Now, what's the explanation? So this is the fun part. We don't know. So you can make the list of kind of general explanations of what it could be. So maybe this guy got it wrong. So that's one question you can test is, are the laws of gravity right? And from the data that we have as of today, well, it looks like the laws of gravity are actually okay. So again, this is based on data from these maps. And so the evidence is actually ruling against modifying Einstein's gravity. And so what we're left with is adding some new force to the fundamental forces of physics. So what most of us learned in school were the 4 fundamental forces in nature. And what we think now is this is incomplete, and there's some new force, some 5th force. And then the question is, what is this? What sort of field is causing this? It could be constant in time and space, or it could be what we call a dynamic field, meaning that it changes with time. And this is where we are in our understanding today. Okay, so one of the things we're trying to do is get more data to try to narrow down the possibilities of what this is. And so this is a project we're working on right now. This is called it's a mouthful, the Dark Energy Spectroscopic Instrument. So this will be in Arizona. And it's the big telescope dome that you see there, where we're building an instrument that's about 20 times more powerful than that Sloan telescope. And I should say this is an engineer's dream, so I don't know what engineers everyone else is working with, because all the best ones, they seem to want to work on this project, because we have 600 tons of moving weight, 200,000 meters of fiber optics. We're building this focal plane for the telescope that has 5,000 little robots crawling around. It's really fun. And what we'll be doing with this is making a much larger map than what we've made previously. So the map that we have today, we've mapped out sparsely about 0.5% of the visible universe. So this is in the however many years, 17 years that I've been doing this. Then with this new telescope, we'll be mapping out This makes it look like a little more than it is, but about 5% of the visible universe. So it's a much bigger fraction of the universe. Okay, then I want to end with this map that we'll be making next, hopefully to understand the next phase of dark energy. So it'll be a map of 30 million galaxies. So it's galaxies and distant quasars. But I just wanted to show this for the kids in the audience so you can figure out how old you're going to be in 2061. So this is a map of how large astronomical maps have been as a function of time. So this was back when I was a student. We had maps of a few thousand galaxies. Now we're up at 2.5 million. This project we're building now will get up to 30 million. And it kind of follows this Moore's law-like projection where if we're smart enough, clever enough, we should get to 140 billion galaxies by 2061. So I invite someone in the audience to do that. Okay, I'm done.
Thank you, David. Presenter number 1. Next up is Haimei Zheng, and she's going to answer the question, when I'm a scientist in 10 years, what will I be able to see with an electron microscope that you or I cannot see now? And again, this is important information you need to have, and I'm very serious about it. Haimei, please come out. Please welcome Haimei.
In nature, how does the caterpillar transform to a butterfly? We can make a guess based on the initial state and end state. Our speculation can be terribly wrong. However, if we watch the dynamic processes directly, there is no ambiguities. In material science, they are full of processes that involve materials transform from one state to another. To understand those problems, including the material's properties, it is important we study the material's transformations directly by direct observation. As a materials scientist, I'm interested in the variety of materials and materials processes in applications for sustainable energy and clean environment. I study materials at the atomic level. Scientists using telescopes to study the large matter, like stars, galaxies. I use a transmission electron microscope to study the smallest matter, the atoms. Transmission electron microscope is a very powerful tool. Even President Obama was amazed by the atoms that can be visualized using a transmission electron microscope. A transmission electron microscope can use the high-energy electron beam and focus the beam using a series of magnetic lenses in high vacuum for imaging. As a comparison to a light microscope, the electron microscope has much better resolution to see small things, atoms, because the electron beam has very small wavelengths. In conventional imaging, using a transmission electron microscope, because of the high vacuum environment, we image materials by drying them out or freezing them. Then, to understand how materials transform from one state to another, we have to do the extrapolation, just like to make a guess on how does the caterpillar transform to a butterfly. Recently, I developed a liquid cell, as shown in this schematic. It can isolate the liquid from the high vacuum environment, so I can study samples, can study materials using the transmission electron microscope. over the years, my students have made several versions of liquid cells. Here I'm going to show you, using the liquid cell, what we can see that was never before possible. This is a movie showing you the growth of small platinum crystal in liquids. You can see majority of these crystals developed into cubic shape. We can also have a closer look at one of these particles. We can see how it developed into a cubic shape. As it rotates at certain angle, we can see the atoms line up. It's really amazing. Thank you. By direct observation, we found the 100-year-old theory for crystal growth is not correct. We found a new rule for the growth of these small particles. Using the liquid cell, we can also address questions in real-world issues, such as batteries. We can make a small battery cell by putting electrodes inside a liquid cell. Then we can monitor the electrode-electrolyte interfaces during charge and discharge using a transmission electron microscope. Then we can see how does the battery work. Mostly, how does it fail? As we're all familiar with the problem, as your cell phone ages, the battery does not take a charge as well. Here is an example. We can image the formation of dendrites during charge and discharge. This damaged the battery. If we understand them better, we can make better batteries. Using the liquid cell, we can also image biological materials in natural water environment. Well, in summary, using liquid cells, we no longer have to guess how materials transform. We can directly observe materials transformations using a transmission electron microscope. This is going to advance our understanding of materials, help us to solve world important problems. Thank you.
Thank you, Haimei. Was I right? This was important for you to know. Okay. Next up, a question close to my heart. Is it possible to power all of San Francisco on ocean wave energy? We're going to find out. Please welcome Marcus Lehmann.
Thank you, and this is a very great question, and people have definitely figured out how to use them to have fun. But I'm here today to tell you why and how we can use them to actually power our homes. And it's a very important question because especially here for San Francisco and California, where the population is expected to double in the next 20 years. And this growing population needs a growing amount of energy. And we have to pay for this energy. Energy is not for free. And so every one of us has to pay the monetary price, but also the environmental price. So California still runs half on natural gas, and we're emitting around 350 million tons CO2 per year. And at the same time, California, we have this ambitious climate and renewable targets. So if we look at these two facts, we can come to the conclusion there's a growing demand and an urgent demand to increase renewable energies. And yet this trend of a growing demand for renewable energies, especially on coastlines, this is not a local trend, this is a global trend. And the US is a great example where half of the population actually lives within 50 miles of the coastline. But to come back to our original question, we have to better understand the resource of waves. And I've been always fascinated by the ocean. I can sit on the beach for hours and stare at the waves. And I'm sure you experience the same while staring in a campfire. And I think we're human. We're so fascinated and hypnotized by both of these natural elements is because there is so much power in there. And to give you an idea how much power are in waves, one ship length of California coastline has as much power as an entire soccer field full of solar panels. And this high power density is the first big advantage of wave energy. The second big advantage is it's the less variability. So the sun only shines during the day. Wave power is available day and nighttime. And the third big advantage is its predictability. So if you want to increase renewable energy percentage in the grid, one of the major hurdles is the predictability. And so wave energy is actually predictable a week in advance, and compared to wind energy, which can change in the order of seconds. So to give you an idea how much power there's actually available, and in the US, we can see that's one of the 4 best spots in the world to harness ocean wave power. And recently, the Department of Energy found out that we could power half of the US just on wave energy. But still, there is not a technical solution there. And so sometimes when engineers struggle and we can't find a solution, then we actually step back and find inspiration in nature. And that was the case with our technology. And here we can see a very special place in the Gulf of Mexico. And you can see on the left side, the big ground swells travel till the coastline, till they break and completely vanish. And on the right side, suddenly all the waves disappear. And this place has been known by fishermen and passed on, and it's called the mud hole. And there is a certain mud floor on this location and this mud hole. And as you can see, as the waves travel over this mud, then the mud starts to vibrate. And then this vibration, similar to a shock absorber in a car, extracts all the energy. So a researcher here at Berkeley, Professor Alam, tried to explain this phenomena. And he created a mathematical model that uses a viscoelastic seabed that's hooked on a grid of springs and dampers. And then he had this great idea, why not using these dampers as generators and then actually produce power with it? And it's quite counterintuitive to have a device being on the bottom, but that was one of the major hurdles of the industry so far, that most of the devices on the surface, they just struggle with the high range of loads and safety factors needed, and these slamming forces and storms coming in. So we saw this great potential of this technology around 2 years ago. So we started building first proof of concept prototype, and there we want to give the credit to our lab neighbor professor who bought the bike pump we used for this experiment. And that wasn't working that well, but then we improved and built a first working model that could actually mimic the mud behavior. And with this device, we could absorb over 80% of the energy. But we didn't get a lot of energy out that we could actually use in a mechanical form. So the last year, we're working hard on developing a system that's actually able to produce a significant amount of energy. And then finally, last summer, we further developed the system and reached over 40%. And that's actually our device working in a wave tank here at Berkeley. And you can see as the waves travel over the carpet, the carpet adopts the wave motion and then drives these pumps which are underneath. And so to give you an understanding of the mechanical principle behind, it works like an hydraulic jack, where a large area and a low pressure gets converted into a high pressure on a small area. And the major challenge was actually to build a material that's able to mimic the mud behavior. And so we used a composite material out of natural rubber and fiberglass, and this material worked pretty well. And then the second big challenge was really to find a generator that would come up with high enough power that we can use. And so we developed a very high flow optimized, efficient, low friction pump. And with this setup then and 3 generators in total, we could convert over 40% hydraulic power. And so since then we improved and built a new generator system that sits on top and then with a way where we can actually control it. And here you can see in this short little clip how effectively our system actually is able to extract the waves. So I replay it in a second, but yeah, look at how much wave is coming in and then how much wave height we actually see after the device. And yeah, we had the fluorescent dye in there because we did visual wave height measurement.
Where's the generator?
And it was on top of the device. And so to better understand the physics behind, we used computational fluid dynamics. And yeah, with this we could simulate the dynamic pressure to better understand the fluid structure interaction. And here we can see as the waves travel over the carpet, these orbital particle motions actually get split into half. And then we have two separate waves, and the upper one gets deeper. And then because of this pressure difference between the upper and the lower one, similar to the pressure difference on the airplane wing, then we can actually use this excitation force to generate power. So let's imagine we upscale one of our units to a 30 by 30 feet unit. And then we place it somewhere south of Ocean Beach where it's not an area of recreational use. One unit of our system would be able to power 180 homes in San Francisco. And this is equivalent to 1,000 barrel oil per year. And to give you an idea how the system works on a bigger scale, here we can see as the waves travel over, the carpet absorbs the waves, and then we generate high pressure ambient salt water that can be brought on shore and then runs a hydraulic motor and can also be used to drive a reverse osmosis chamber to create fresh water. And that's actually, especially for California facing the droughts in the last couple of years, a great application to use a renewable source for desalination. And our system in general has three major advantages. The first one is the higher survivability. As we heard, the major drawbacks in the industry were the high slamming forces on the surface. So the fact that the system can work efficient, submerged, is the major first advantage. The second is the higher efficiency, because we're based on this natural phenomena. And at the same time, there's a trend that we see in the wind energy industry where the wind blades get bigger and bigger. And so similar, our device has the capability to upscale because the power of the waves in the width. And the last advantage is the visual impact. So the fact that it's submerged just comes with this major advantage. So what's next? We're very happy about our progress and excited about our next steps. We're working towards the first ocean pilot and at the same time optimizing the system for full-scale integration into the grid. And so we're happy to be supported by the Berkeley Labs that attracts some of the best engineers and scientists in the world. So on all aspects of the simulation, engineering, but then also the bigger questions, we find experts to talk to. And then we got integrated into a great new program called the Cyclotron Road since last year, and we get great support and mentorship there. So now that we better understand the resource and the technology, we can come back to our original question, and we can have a closer look at San Francisco. Here we can see the average annual wave power is quite seasonal, but in average it has around 20 kilowatts per meter. So again, it's 30 times higher than wind and solar. So with a strip of, single strip of 33 miles and a device like ours that works at 60% efficiency, we could power entire San Francisco. So because of the huge potential of the technology, we were won the first prize of the Berkeley Resource and Energy Collaborative the last 2 years, and were awarded by MIT and Caltech Clean Energy Prize. And the National Geographic named us one of the 5 striking concepts of harnessed wave energy. And so we want to thank everyone at UC Berkeley that supported our progress so far, and then Science TV for these great video shots. And because it's very hard to find funding for renewable energy, and we did a crowdfunding campaign last year, so we want to thank all our backers as well. So to get back to our final question, to our initial question, our final answer is yes, we can, but it has to be in a mix of renewables. So similar to a good farmer, we have to have a healthy mix and use all locally available resources. So please visit us at calwave.org or at Cyclotron Road, and then we hope to see you at our first installation in San Francisco in the next couple of years.
Thank you, Marcus. So for some of you who have seen our 8 big ideas, we have a timer up here for 8 minutes. We didn't do that this time. We gave the scientists a little more time, but they worked very hard to make these shorter and digestible. So let's give a round of applause for them so far. I think they've done well. And just a reminder, if you're tempted to ask a question during the presentation, please don't do so. We do have a Q&A session where you can line up and ask questions appropriately. Thank you so much. Okay, next. Lara Kueppers talking about climate change. Is it going to kill the forests in California? This, again, is something we need to know. Lara, please come on stage.
This is a pretty depressing question I got. So, no, luckily, climate change. So luckily, climate change will not kill all the forests in California, but we do expect it to cause quite a few changes as we move forward over the coming century and longer. So the most certain change for climate change in California is higher temperatures, and I'm sure you're all familiar with pictures like this that show the increasing temperatures expected over the next 100 years or so. So this shows about a 5-degree Fahrenheit increase in Berkeley, and as you move inland into those redder areas, we're expecting larger temperature changes. The projections from global climate models for precipitation change are relatively small, and they're pretty uncertain. But what we do know is that with warmer temperatures and no increase in precipitation, we expect the summers to be drier. And this is important for plants that grow in your garden, that grow in our fields, and that grow in our forests. So over many years, decades, scientists have been returning to measure individual plots of forest in California and other places in the western US, and have seen increases in mortality of trees. Over about a single generation, a human generation, we've seen a doubling in tree mortality as a consequence of warming temperatures and this increased summer water stress. And what we've been looking at here is background mortality. So this is just simply sort of the year-by-year turnover of trees in a forest that's been increasing. But at the same time, we also have seen that warming temperatures and increased drought stress also increase the rate or the extent to which insect outbreaks like bark beetles, shown in this upper panel photo here, have killed patches of forest. And also, warming temperatures increase the frequency and intensity of large wildfires. So while this all sounds pretty dire, luckily the death of trees does not mean the end of forests. But it does mean that we can anticipate quite a few changes moving forward. So one of the answers, I guess, to that original question regarding whether all the forests will die is that many tree species will not grow where they grow today. This is a change that we know to be with a good amount of certainty. So the example I'm showing here is for a species called blue oak, which is widespread in California. It forms a bathtub ring around the Central Valley. And it's endemic to our state, meaning it grows nowhere else on Earth. When we used some climate change scenarios to anticipate where the climate suitable for blue oak will be in the future, we see pretty dramatic shifts. In the light green colors, what I'm showing are areas where this habitat that's suitable for blue oak is eliminated in a future climate, warmer climate. And in the dark green areas is where I'm showing newly suitable habitat or habitat that remains suitable over the coming 100 years. And so what you can see is that there's a large amount of area that's been eliminated from the current range of this species. And then there are areas higher in elevation and to the north in California that will be suitable in the future. So we've made these kinds of predictions. Myself and other scientists have put together these kinds of projections for many, many species. And they all paint the same picture, which is that species will need to relocate to stay within their climate zone. So another question that I've been pursuing recently is trying to address this question of whether alpine treeline will move upslope with climate change. So the uppermost elevation limit of forests tends to be where the temperatures in the summertime are around 40 degrees Fahrenheit. And so we expect that with warming, trees will shift upslope to take advantage of the warmer temperatures, displacing the wildflowers that are currently growing in these alpine areas in the summer. To learn more about whether these trees will establish in the alpine habitat, we're using heaters suspended from these poles here to actually physically warm seedlings that are sown in plots, in garden plots in the alpine tundra. And what we're finding is that water stress, as I mentioned earlier, is even a factor here for trees establishing at the coldest edge of their range. And so, in fact, what we found is that while the warming, the heating that we're doing alleviates the stress that comes from cold and frost, it actually exacerbates the stress that comes from drier soils. And as a consequence, the seedlings in the warmed plots don't really do any better than the seedlings in the unwarmed plots in terms of their growth and survival. This is something that we weren't expecting, given our understanding of what controls this cold edge limit of forests. More importantly, however, though, than this interplay between temperature and moisture is the fact that for seeds to arrive in an alpine environment like this and grow up into a forest takes hundreds of years. And so while mortality, a big mortality event might kill off a patch of forest in as few as 5 or 10 years, for example, as a consequence of a big insect outbreak or a large forest fire, it will take hundreds of years for that forest to regrow or for forests to establish up at higher elevations, like in this alpine site. So another effect of climate change on forests is that future forests will function differently than today's forest. And by function, what I mean is the cycles of water, carbon, and nutrients in the forest will happen somewhat differently. And we know less about how these changes will take place than we know about where species are likely to move to. So a reason we care a lot about how forests will function differently is because forests exchange vast amounts of carbon dioxide with the atmosphere each year. And in particular, tropical forests, like I'm showing here, take up about 1/3 of the carbon pollution that we emit each year. And so understanding how these forests will continue to take this carbon dioxide out of the atmosphere is critically important for projections of future climate. But we have a really big challenge, and that is that tropical forests in particular are extremely diverse. You can have thousands of species in any given forest in the tropics. And the models that we have today that model forest function on a global scale really don't account for that diversity at all, in fact. And this is a problem because without accounting for that diversity, we're not accounting for how different tree species might respond differently to climate, enabling a forest to be more resilient than we might think it is. And so one approach that scientists are beginning to use, including at Berkeley Labs, is to take advantage of what we know, what we know about the characters or traits of species that enable them to survive or even thrive in different environments. So a trait might be how fast a tree grows. Some trees grow fast while others grow slowly. Some trees require a lot of nutrients while others can get by on infertile soils. These traits also have trade-offs. And so, for example, a fast-growing tree typically requires a lot of nutrients. So a large new initiative led by scientists at Berkeley Lab is taking up this challenge of modeling the change in carbon functioning of tropical forests by using this trait-based or trait-enabled approach to predicting the future of climate change, of carbon cycle change in these forests under climate change. So unfortunately, I don't have an answer for you tonight, really just an ongoing question and research area that we're pursuing. So finally, I wanted to mention the fact that I care a lot about how forests change, in part because forests affect how the climate will change. So as I mentioned previously, forests absorb and re-release vast amounts of carbon dioxide into the atmosphere each year. And in fact, about a half of the emissions of carbon dioxide from humans, carbon pollution, is taken up by these forests each year. But at the same time, deforestation and forest degradation contributes about a third of our total carbon pollution. So these forests are very dynamically involved in the carbon cycle globally, and the amount of carbon that remains in the atmosphere is what influences and is continuing to influence our climate over time. So we're studying how climate change will alter these forests, but also how these forests affect the climate system by taking up carbon through photosynthesis, by storing it away for decades or centuries in wood and soils, and releasing it back to the atmosphere through the decay of leaves and roots and wood. Another way in which forests affect the climate system is through their effects on energy and water budgets at the Earth's surface. So forests tend to be darker than other ecosystems. You can actually see this effect from an airplane window. And this means that they absorb more of the solar radiation coming in at the Earth's surface. And this tends to warm the local area relative to in a more reflective ecosystem. In addition, forests have a lot of leaves, and they have very deep roots. And this means that they can effectively move water from soils into the atmosphere. And this actually tends to cool the local climate because it's like water evaporating off of your skin. It has a cooling effect on the temperature. So the ecosystem shifts, or the forest shifts that I spoke about earlier, actually have the potential to affect the climate locally where we live. We used a climate model to anticipate how a change in vegetation that comes from a change in climate contributes to local climate change that we would feel here in California. And what we found is that these shifting ecosystems can have a very large effect, amplifying the original climate change or dampening it. In this image here, the darker colors show where that effect of the vegetation change is as large as the effect of the original climate change. So in the dark red colors, the climate change is doubled, and in the dark blue colors, it's completely eliminated. And so what you can see here, when we add it all up, was that the climate change that comes from vegetation change can account for up to 70% of the total change. So this is what we call a feedback effect from changing vegetation and climate together. So forests play critical roles in the global carbon cycle. They provide habitat and resources for animals. They affect our local climate. And they also, of course, provide economic and cultural resources to all of us. So I think that it's important to continue to study the ways in which climate change will affect these forests and the way in which forests affect the climate in order to better predict the future of both. Thank you very much.
Thank you, Lara. Well, one of the wonderful things about putting this program together was the great diversity of questions that we were able to feature tonight. And the last question for the last presentation is, what can a tabletop accelerator do that a big one like the LHC can't do. Our presenter, Wim Leemans, is about to answer that question for you. Wim, please join. Yes.
Okay, so let me tell you a little bit first about the accelerators. Accelerators come in many sizes and energies. Very low energy accelerator is shown here. This is roughly 10 kilovolt. Some people call this a television. If you go to the dentist's office and you get an x-ray taken of your teeth, you actually sit in front of a little accelerator that puts out something on the order of a few tens of kilovolt to take a nice picture of your smile as you're sitting in a chair being tortured by your dentist. And then at the lower energy, still, you have these devices here, and they're used for vulcanizing our tires, for making radioisotopes, for important applications to society. In the lower part of the screen here, I will show you a couple accelerators that are more discovery tools. Here at Berkeley, we have one of the best in the world X-ray sources based on an accelerator. Beam goes around in a circle, and as it goes around in a circle, it emits light. At SLAC, back in the 60s, they built an accelerator which was 2 miles long. If you drive on 280, you drive actually over the accelerator. And so this was 2 miles long to reach 50 GeV in our language, or 50 billion volt. And then at CERN, of course, there is the largest machine to date, 27 kilometers circumference, where they're colliding protons on each other to discover new particles like the Higgs boson, and really do forefront discovery science in particle physics. And so when you think about the story here, Berkeley Lab was founded by Ernest Orlando Lawrence, and he's holding the first cyclotron in his hand. And about 80-some years later, people are building machines that are the size of a small country, at least a small European country, with a stored energy in this is megajoule, 300 megajoule. And to give you a sense of what that means, if you're sitting on the TGV to go to CERN, at 150 kilometers an hour, that represents 360 megajoule. If you're, I don't know if anyone in the audience ever has been on an aircraft carrier, I certainly haven't. But if these things go at 12 knots, it's 360 megajoules. So it gives you a sense of what the community has done to go from a handheld device to this gigantic machine with which people discover new things. So we asked ourselves the question, can we make them smaller again? And so if you think about what happened in computers, computers shrunk. And if we would be still in this era here of the supercomputer from 1954, I would have to have a gigantic pocket to hold my iPhone in, right? Instead, we're now carrying around computers that are far, far more powerful. So the question that we look at is, can the same be done with particle accelerators? So how do we go about thinking this through? So increasing the power inside a conventional accelerator, you could say, well, look, the particles get accelerated by electric fields. Just crank up the electric field to reach higher energy electron beams. Well, eventually it will lead to sparks in your accelerator. And I know my wife is in the audience, I want to tell her if the microwave oven doesn't work in the next few days, it had nothing to do with the making of this movie. So here is a microwave oven, and you put some aluminum foil in it, and this is what happens. So it's pure coincidence, honey, if ours doesn't work anymore. So to think about accelerators in a different way, let's think about a favorite pastime for some people. Surfing behind a boat. So here you have a brave guy surfing behind this boat here. So this boat is exciting a wave on the water, and he's actually riding that wave. So what we are working on is essentially the equivalent, but we replace, here you see again the same picture. You have your boat traveling over the water, exciting this wave, and this guy is surfing on it. So what we do is we think of our surfers as electrons. Our boat is actually a laser pulse. And the liquid, the equivalent of the liquid that the laser pulse has to go through is called a plasma. And this is not the plasma that runs through your body. This is a very different plasma. This is an ionized gas. This is electrons and ions freely streaming around. And what you're doing is, when you send in this intense laser pulse, and I mean intense, it's of the order of, in my units, 10 to the 18 watts per square centimeter. So it's enormously intense. If you send that into this liquid of electrons and ions, the electrons get pushed out of the way by like a snowplow, and the ions are left unshielded. Now the ions pull the electrons back, and what you've set up is a clump of negative charge and a clump of positive charge. It's like a traveling battery behind the laser pulse. And the fields that you excite in here are of the order of 10 to 100 billion volts per meter. So this is already broken down, basically. You don't have to do your microwave thing to break this thing down. It is an ionized gas. It is, per definition, already ionized. All you're doing is you're moving charges around and you're creating a wave to allow these electrons to surf on. Here are the electrons. This is the laser pulse. This is a simulation on our supercomputer. And behind the laser pulse, you see this wave. And the color change indicates the energy gain of these electrons. So we can actually simulate this. And of course, we did this in the laboratory as well. I know this movie went by really fast. But red here is 10 billion volt. And this is of the order of 6 billion volt. And this is done in a distance of about 20 centimeters. In fact, I never leave home without my accelerator. Here it is, in case I have to revulcanize my tires, create some radioisotopes, call me or find me after the show to discuss. There's offers to be made. So now to do this correctly, you have to have some control because you have this wave. How do you get your servers onto this wave? And that's the tricky part. So if you look at these guys here, they're beautifully riding this wave. We're exciting it. And we call these the injected electrons. And then you have this unlucky fellow here. He's injected out of phase. He ain't making it today. So we use these guys, and that takes really good control of all of these laser properties and plasma properties, etc. And so it takes a lot of work. We have the world's highest repetition rate, highest peak power laser here on the hill. This is a laser that produces about 1,000,000 billion watts, but in a tiny, tiny fraction of a second. In fact, it produces it only for about 50 femtoseconds. So that's a 0 and then another 14 zeros and then a 5. So otherwise, you would see the lights dim every time we fire everywhere in the Bay Area. That obviously doesn't happen because we store the energy and then we release the energy, and we do all of these gymnastics on the laser pulse. The other thing we had to invent was, with our help from colleagues at Oxford University, is this structure, like the one I have in my pocket here. This is actually a hydrogen plasma. This is a real picture of the real device, the hydrogen plasma. And you can see the plume flowing out here. This is live action. Laser pulse gets coupled in, and if you do things right, you get these ultra-high energy electron beams. And we have right now the world record at Berkeley Lab, 4.25 billion volt in 9 centimeters. So this is clearly a tabletop part. The laser, I grant you, that's not quite tabletop. But if you think about what we're doing is, if I would try to do the same with conventional technology to reach 10 billion volt, I would need at least 5 football fields. To do what we did, we built this lab. This is the laser here. This is the target chamber. And this is our friend. It fits in there nicely. And to put this on scale compared to the football fields, that's what it looks like. So of course, when you think about these discovery machines, you also try to make sure that when you talk to your neighbor, you can actually tell your neighbor you're doing something useful, right? So I was at an evening giving a lecture in San Jose, and they asked me, have you ever thought about putting an accelerator inside the body? And the reason you would want to do this is if you're so unlucky to have cancer, where they need to put radioisotopes in your body to treat the tumor, what happens is, if you look at the prostate here, you have your tumor here and you implant radioisotopes, you'll irradiate not just the prostate, but you'll irradiate a broader bulk of the tissue that's all surrounding it. So what they asked me to do is, can you think of a way to build an accelerator that actually would go into the body, produce these electrons, produce the radioisotopes right there in situ, you pull your accelerator out and you're done. So we first thought, I must be honest, I first thought that was a little crazy, but even for me. But so we decided to think about it, and I have a brilliant postdoc and a wonderful student as well. And so we decided, let's think about a fiber optic, a special fiber optic that can deliver laser power onto a special little tip here, where the tip contains gas that you deliver in through this fiber, and you make sure that your gas has a very sharp threshold. Think now about waves on the ocean. If you're sitting at the beach and you have a rock, and the wave comes over, the wave is going to break over that rock. When the water breaks, that's when the electrons get released, and they actually can produce a little electron beam. So our dream is to build this thing, and this is meant to be a finger. I know this is a little bit confusing, but the rice grain right there, that would be the size of the accelerator. Right now, we have done the reverse of what people do that build airplanes. When you build an airplane, you start with a model, and then you go to the big scale. We're a little doing the reverse here, because I don't think anyone wants to put our prototype in their body. So this is scaled version so that you would see it. No, I'm kidding. We need to make it smaller, obviously, but this allows us to figure out how do you make a profile like this. And so this is really fun work to do, because this would be an incredible feat of sort of engineering, physics, and it really is the story of science. You start with a very lofty goal, with a moonshot, and then you come to something that maybe actually be very practical. So I like to end here with this same picture as I showed in the beginning, but this time with a provocative quote that I like to stir things up when I'm talking to my funding agencies or anybody else. Those that say it cannot be done should not interrupt those that are doing it, from George Bernard Shaw. Thank you.
So thank you, Wim. How about a round of applause for all of our 5 science presenters? So, David, what's the most frequent question people ask you about dark energy while we're waiting?
See, every question I get's hard.
That shouldn't be a hard one.
The most frequent question. Well, I guess I often get the question of what is it?
Yeah.
And that's both a hard question and an easy question. It's an easy question because we have no idea. So that's the short answer. And then I can give you a longer answer.
So does someone ask you, is this the scientist's full employment act to look at dark energy at the end of your career?
Right. Well, it's, how much time do we have here?
That's okay. We're waiting. We're doing some hand counting of the ballots, so to add to the list. So we have a second.
Okay. Well, I can talk for a couple minutes then.
Okay.
So we're pretty much in the very early days of dark energy, where it's been discovered. We have no idea what it is. We have basically one theory per day in the literature. So you could ask me about your favorite theory that you've seen, and odds are I haven't read it just because there are so many. But I kind of liken it to our understanding of dark energy today. It's where our understanding of general relativity was in 1704, which was, well, that date means something. So that was 17 years after Newton published his laws of gravity. And they fit almost everything except for one little piece, which was the orbit of Mercury. And so that was a puzzle that lasted for actually about 200 years, more than 200 years, until Einstein explained it. And so for dark energy, you know, maybe it's like 1704, we have this one little puzzle of the geometry of the universe not being quite right, and we're starting to pick away at it, and maybe we'll figure it out next year, or maybe we'll figure it out in 2234.
Yeah. Okay, let's start with this gentleman right here to my left.
How do you protect something underwater from seawater, from the corrosive effect of salt?
Marcus, that's for you, yes. It's definitely not for me.
So that's a very good question, and we're happy that the oil industry, offshore oil and gas.
Yes, it was about the corrosive nature of salt. How do you protect against that?
Yeah, so yeah, we talked to actually the CTO from the former CTO from the Navy, and he said to tackle the corrosion problem is answered by the number of coating layers you use on your marine grade steel.
The standard candle, as I understand, works by comparing the spectrum of the supernova that's really far away to the brightness. How do you know that the spectrum hasn't changed because it's going through that expanding space-time? I mean, all you really know is that it's accelerating. I mean, how do you? Where is it about the darkness of it?
Right. No, so, yep. So I think I have the question here. So the question is, how do we know from these supernova that it's right, that we're interpreting it correctly here? And the first thing I should tell you is I think I was the last person in astronomy or physics to believe it. So when the history books write this as a discovery in 1998, when did I believe it? 2004, maybe? And the reason is there are lots of possible explanations for this. And so one of them actually is the same explanation that they tried to use for Newton's laws not being right, which was, well, maybe there's some dust in the solar system, and that's slowing down the motion of Mercury, and that could explain what was happening to its orbit. So with these supernovae being faint, one of the possible explanations was, well, maybe there's some dust between us and these supernovae, and that makes them look a little bit different. And there are other possible explanations, but what we have had since then are completely independent measures that agree precisely with these supernova measures. So what I was showing with these galaxy maps, we're making this three-dimensional map, and the third dimension, what we're actually making is we're making a map where there are 2 dimensions in angle. Then there's a third dimension where we measure what's called the redshift, which is the recession velocity of a galaxy. And we have to convert that to a physical distance. And there's only one way to do that conversion where you get a geometry that makes sense. And so it turns out we actually have 3 or 4 methods now that agree precisely with that supernova memeasurement.
How do we know that?
Thank you for your question. I'm sorry, we have quite a few people. Could you can maybe hold it and talk to David afterwards? Thank you. Could we take the question upstairs, please?
Oh, sorry. Hello. I had a question on the wave technology. So I know there are lots of organisms that depend on the surf and the interaction of waves at the shoreline. I noticed that your mechanism reduces the amount of waves that arrive at the shoreline. I'm curious if later in this research that you plan to use marine biologists and people like that to understand the impact there.
Yeah, we're actually in touch with several marine biologists. There's a great Professor Mimi Cole from Berkeley, and then also the Bodega Bay Marine Laboratory. And so it depends on how much, like what size of unit you use, and of course if you would potentially absorb the entire amount of energy, then you would pretty much turn the natural habitat from a splash zone into a harbor zone, similar to the bay bay habitat. But in our case, I think this will not be the major problem because the energy density is so high that we will never extract such a high amount. So there will be always waves coming in.
Thank you for your question. I think we have a young man right up here. That's the next question.
Yes. On the topic of electron microscopes, why use electrons? Because if you have a positively charged particle, let's say an alpha particle, that would allow you to localize atoms much more easily because you would be able to actually detect the nucleus instead of have very slight deflections.
Haimei.
That's a hard question. Well, the electron microscope, we use very high energy electron beam. So these electrons pass through the sample. So the interaction between the electrons and the particle is not like what you imagined, the positive charge, negative charge. The energy is just so high, it passes through directly. So the diffraction is dependent on whether it lost energy or not lost energy. There are technical terms on that. Maybe I can explain you more later.
Right, if you want to stay around and you can ask more probing questions if you're following the show. Thank you so much for your question. This gentleman here has been waiting patiently.
This question is also for Dr. Zheng. I think what you have done with your liquid cell technology is marvelous in shielding what you're looking at from the vacuum so that changes can occur. At least if I understand what you've done, that's it. But to look at things at an atomic scale, it has always been my understanding that you need a scanning tunneling electron microscope. Is this a new form of electron microscope that will look at atomic scales without the needle and the tunneling effect and all of that?
Well, this is not the transmission. This is not the tunneling microscope. It is the transmission electron microscope that has been invented since 1931. All the time, we have been imaging materials in high vacuum environment. It's the first time we were able to see materials in liquids, but using the conventional microscope.
But it has been possible since then, for that long, to see atoms?
It has always been we have always been able to image materials in atomic resolution, see the atoms since the 1980s.
Thank you very much.
Thank you very much for your question. This gentleman right here.
This is a question for David. So I just need a little clarification on the dark energy, because up till now everybody's always been saying dark matter, dark matter. So is now what you're explaining is dark energy. Dark matter is actually one of the possible answers for dark energy?
No, so this is, okay, so that's a good question, the difference between dark matter and dark energy. And I should have said there's one thing we know about dark energy, which is it's not a particle. Then that's about everything that we know. But what that means, I mean, you're bringing up the point where it's not just this one enigma in fundamental physics right now, but there are two completely different phenomena here to be explained that we know very little about. And one are the dark matter, whatever the dark matter is, which we know is a particle, and then dark energy, which we know is not a particle. And again, it could be a field, it could be changes to gravity, although the most recent data says it's not. But there are two phenomena that we're talking about. And then that's about everything we know.
So you're sure there's two phenomena, there's not one phenomenon causing both the differences? I guess I'll let you think about that. It's a little
It is confusing. Next question upstairs. I think I see someone up there.
If we understood dark energy...
Did you say who your question is for? Is it for...
Oh, it's for...
For our dark energy expert?
If we understood dark energy, what would be the applications?
Sorry, I just missed the very beginning there. if we understood dark energy, what would the application be? That is a very good question.
We didn't ask that one today.
And I wish I had an answer for you. I mean, it could be so many different things that, I mean, I'm sorry, I just don't have a good answer. But I mean, what we can do is we can look at historically the discovery of general relativity wasn't immediately obviously something that had any application. So it's not impossible to imagine, but other than that, I can't tell you.
Great question, thank you. Another question from upstairs.
Yes, I got three, starting with astrophysics. Could we possibly one day use dark energy to power a starship? And the other two would be for Tabletop. What delivery system is used for gases and dose meters? And then the third for climate change. What can we use for from all the cultures that have come across these problems before that have survived, whereas some empires have fallen?
Let's do it in reverse order. Lara, why don't you answer the question first, the climate change question?
I have to say I didn't catch the climate change question. Sorry.
We've been through this before, yes. And it's brought down other empires where others have survived. Which could we learn from history there that would help us out? And then for the dose meter,
that's good. I think we have the others.
Yeah.
Okay, go ahead, Lara.
Well, that's true. The climate has changed pretty dramatically in the past. We've had ice ages, and we actually can look at pollen records that have basically tracked the migration of tree species as the ice sheets have retreated, for example, following the last ice age, and seen that trees do indeed keep up with their climate zone as the ice sheets retreat. But it's also the case that those species had really thousands of years to adjust to a changing climate. And really one of the big uncertainties that we have today is not if species will shift in their distributions, but it's how fast can they move. And we anticipate the climate changes over the coming century or centuries to be much, much more rapid than we've seen in the record, the paleo record and the historic record. So it's a bit of an open question in terms of you know, how fast things can adjust.
I think we're just going to take one of your other two, and that was the question about the accelerators, since we hasn't had a chance.
Astrophysics, yes. Could we use that possibly as in building our first starship?
That's for David. That's not for me.
All right.
I'll take it.
Starship.
And I appreciate the moderator's attempt to give me a little more time to think about it, which hasn't helped very much. So what I can tell you is I'm not aware of any of the possible explanations for dark energy that would essentially allow us to harvest that energy. But what I can tell you is actually that dark energy, it does dominate what we call the energy density of the universe today. So meaning if you interpret it as an energy in the universe and add up all the energy from other forces and particles and so forth, it does dominate by about 2 to 1. On the other hand, the density of dark energy within kind of the volume of the Earth, it's actually quite small because on average the universe is pretty empty. So even if you could imagine something like, oh, somehow we're doing something where we're harvesting all of the dark energy that we can find on the planet, it wouldn't actually add up to very much.
Thank you. Gentleman over here, please.
You know, we always start with our assumptions, and astrophysics is sort of crippled by, to me, by this huge assumption that the basic laws of physics are uniform throughout the whole universe, and I don't see any reason why we should believe that. And if you throw that up in the air and say we cannot assume that 8 billion years ago the laws were the same, can you do any work in astrophysics if you let go of that assumption?
No, so that is a great question. And so part of the answer is we can actually test many of the laws of physics back to when the universe was just seconds old, because that influenced how atoms and the elements formed. And by changing many of the laws of physics, the coupling constants and so forth, even by a little bit, the world would not have evolved as it has today. So we would have different amounts of hydrogen and helium and so forth. So actually we effectively probe back to when the universe was minutes old just by looking at the composition of the universe today. However, what I'll tell you is with dark energy, it could very well be different in some extreme position, go 10 billion light years in that direction and 10 billion light years in that direction. That's not tested today. So I said dark energy, it might be a dynamic field, meaning that it's something that's changing with time, and I expect it probably is. It could also be different in very different regions of space, and as of today, that's pretty much untested.
Thanks for your question. Next question over here.
Hi, this question is for Marcus. I'm wondering, given what you know right now about getting energy from waves, what features of cosines would be the most ideal situation to have that technology installed? Because I imagine with all of the hurricanes that hit the lower parts of the United States and things like that, it might not be as feasible to install something that elaborate down there.
Yeah, so I would say the first we would go in the regions with the highest energy density. So if we look at the northern states like Alaska and Oregon, they have a very great resource, but also California. So it's mainly the West Coast because the origin of waves is actually, it all comes from the sun originally, and then that creates a temperature difference that ends up in wind, and then wind creates friction on the water, and then it's actually the wind that produces the waves. So the big and the good locations are always on the West Coast in Europe and the US or in Australia.
Thank you. Let's take a question up above here.
Mine is also for Marcus. I was wondering about the salmon, the crab, and the halibut. What happened to those in your project?
Yeah, every time you build something, you have to take the environmental impact into account. And so one aspect we're working on is the structure of the surface itself. And in our latest conversation with a marine biologist, we considered the option of actually allowing as much growth as we want, because there might be a chance that the rougher surface of the carpet ends up improving our absorption efficiency. And so it could even be, because the only working parts we have is the shaft of the hydraulic cylinders. So it could generate even more habitat for different forms. And then in terms of the bigger mammals, of course, that's one thing you have to address. And that's very strict investigated. And so there we're expecting, because we don't have fast moving parts, so in general renewable energy with moving components, it's the speed that the animals are not familiar with. So with wind and tidal, they have very fast moving blades. But in our case, we're moving as fast as the ambient water particles. So only slow-moving components. Yeah.
Thanks for your question. I can't tell, is there another question up here? Yes, okay.
How much would the research and development for that grain of rice size particle accelerator cost approximately?
Finally, a question for Wim, yay.
Well, how much money do you have?
You might be surprised.
Yeah. If there's any donors in the room, please see me after the show. Well, right now, of course, for the big devices, the discovery machines, the hope is that our technology would reduce the cost by at least an order of magnitude. So they would still be very expensive machines of the order of $1 billion to build them. We are working right now on really the base technology, making sure that we can make all the surfers behave properly and inject them nicely. We're also working on experiments where we take one module, produce beam, and then couple that beam into a second module. Because that's, after all, what they do in conventional accelerators. They take the beam and keep on accelerating it, structure after structure. The problem is it's 2 miles or more, and that's what we try to solve. So that's where the R&D is. The laser technology itself also has to really undergo revolutionary change, I think, because if the lasers that we use right now, they consume a lot of energy because they're done in a very inefficient way. But when you think about your laser pointer, when you think about the fact that every car in the world right now is being welded, not electrically, but by lasers. And the reason is they figured out that if you build fiber-based lasers and you do diode pumping, you can get exceptionally efficient, very, very high average power systems. So we're hoping that that technology that's now building our Toyotas and our whatever, Hondas and Mercedes and so on, that technology will also translate into lasers that will be useful for particle acceleration. So it's still a ways off for production machines, but we're having a lot of fun with it.
Thanks for your great question. Next question here.
I took a course in electron microscopy about 30 years ago, and I actually hated it because it always, back then you were always, it seemed to me anyway, that you're always really looking at an artifact. So I found your talk really, really interesting because, well, speaking of artifacts, how do you know that the high energy created by the electron beam passing through the liquid and the object that you're studying isn't influencing the phenomenon that you're observing?
That's a great question. So we don't know. We assess each system. One way to do it is we control the electron beam dosage. If we look at the reaction is dose dependent, it is affected by the electron beam. But if the reaction is not dose dependent, in that case, the electron beam is not driving the reaction. There are many other ways. For example, we can look at the material, look at the materials transformations using the electron microscope. Then we can use other methods, for example, X-ray, or other methods to just to confirm what we observed is true. So that is a very great question. We take very careful measurement to a lot of control experiments.
Thank you. Next question here. We're going to do probably 4 more. I'm sorry because we don't want to run over. I'm conscious of the time. It's getting closer to 9 o'clock. So we'll take this question and we'll do a few more. And then you can ask the scientist questions after the show as well. Please.
This is a question for Laura, I think. So I don't want to start a debate or anything, but I'm just wondering what your thought is on the whole ocean wave technology and how that might affect the ecology on the shoreline.
Ooh, now that's interesting.
How many carbon emissions can you offset with ocean wave technology?
1,000 barrel oil per year with 1 unit.
Something. Yeah, I mean, I think one of the big challenges with any kind of renewable energy technology, and we probably need all of them all together, is that the challenge of overcoming the energy supply that we currently depend on it's a 9 petagram a year problem of carbon problem, which is a lot of carbon. And so there are people, other people at the lab I know who study this very carefully and who come to the conclusion that we need all of these strategies combined in order to keep our carbon emissions low enough that the temperature change will stay within, say, a 2-degree threshold, which is considered by many scientists to be kind of a critical threshold for Earth system change. So unfortunately, there's not a silver bullet or a silver wave generator.
Thank you.
Marcus, do you have anything to add to that?
Yeah, I think it's also, if you look at the math, how much CO2 results in how much temperature increase of global warming. then you come to the conclusion that we just have to leave some of the carbon down there, and we just have to stop pulling all of it out. And yeah, that's kind of our conclusion. So of course we need generation technologies, but also we can just leave some down there to really stay to the 5 degrees increase.
Okay, thanks. Let's do the next two people here on this side.
I had a question for David. Saw that look. But do we know with our current measurements, like the densest parts of black matter in the universal map? And if so, like, are the densest parts, like, do they revolve around like the biggest celestial things like in our universe?
Sorry, I think again I missed the beginning of your question.
Okay. Do we, with our current measurements, do we know where the most densest parts of dark energy are in the current map? And do they revolve around large celestial like objects of matter?
Right, so the so with dark matter, we're actually at the point where we can map out where it is on scales of galaxies and clusters of galaxies, because we can see its effect gravitationally. With dark energy, we basically just have a handful of measurements in the whole universe right now. And so locally, meaning just within, where this is the astronomy local, where we talk about, oh yeah, in our backyard. Well, the backyard for us is, well, in the nearest 10,000 galaxies. In that backyard, we don't really have any measure of dark energy whatsoever, and that's just because it's, whatever the effects are, it's actually overwhelmed by just gravitational forces. So it's really only by making maps on much larger scales that we get to see it at all to any precision. So I know that's an unsatisfactory answer, but that's all we have.
Yes.
Hi. I have a somewhat of a general question, and I'm a big believer in the fact that, in 20 years or so, we will have, electron microscopes that are advanced enough that we see what's going on, and I'm a big believer that we will have the tabletop particle accelerators where we get to fuse our own particles and experiment around. So something that I find very interesting is, my question is, how can we responsibly and safely let the general public use these new technologies? How do we ensure that we're using them safely and responsible way? Because a parallel that I see today is, for example, 3D printing, where what used to take a whole factory to manufacture parts have now shrunk to a point where you can print plastic parts at home, manufacture your own parts, components. So we're miniaturizing all of these technologies, and I'm a big believer that it's happening at a fast enough clip where the general public can really easily have access to all these great technologies. So
okay, I think we're going to have Wim answer that one. Go for it, Wim.
Well, should there be an accelerator in everybody's pocket? That's what you're asking me, sort of. The technology that we're working on is still requires really skilled people to operate the devices. My hope and my dream is that this fiber optic based accelerator would go into hospitals, would go into treatment places, but they would still be handled by people that actually know what they're doing. There is a lot of power in these devices, and it is certainly dangerous technology if you don't control it. But at the same time, I think it's technology that will enable so many things that are very important to society, that thinking through what are the limits to the technology and how should it be made available, etc. It's certainly an important question, but you always have to have sort of the benefits against the bad part of technology.
Thanks for the question. So I want to ask one of Lara before we close, which is, what is the fate of the coastal redwoods? Can you tell at this point?
The fate of coastal redwoods?
Mm-hmm. Fate.
No. I can't tell you. You know, redwoods are a really interesting case because they've been around for thousands of years. They're really ancient lineage, and they've managed to hang on through quite a lot of variations in climate. And in California, where they are today, the coastal redwoods sort of hug the coast for a reason, and that is that they're very sensitive to water loss. So we can keep them alive in the Central Valley pretty well by watering them constantly, but the second you turn off the irrigation, they're toast. And so they really like that cool coastal climate. One of the really interesting challenges of predicting the future of coast redwoods, sorry to make a short question a long answer, is that one of the things we don't know about climate change is whether that fog off the coast of California is going to be intensified or weakened. And so if it's intensified, actually the coast redwoods are in pretty good shape. But if it's weakened, their range is likely to shift along with all of the other species. So we're working on that. We do see that where it's hot in the historical record over much of California, we tend to have less fog on the coast in a particular year. But whether that's a good projection for climate change into the future, 30 or 40 or 100 years, actually still remains to be seen. Getting climate models down to that fine resolution that they can simulate fog will be a real advance for us.
Thank you. Okay, well, it's a sorry note, but we're going to close the evening now. Thank you, Berkeley Lab scientists. Thank you, audience, for your participation and for coming out. We appreciate it, and please come to see us in Oakland on April 29th. Thank you again.